Welcome to the UGC EPG Pathshala lecture series in computer science. In this series of lectures, we have been looking at database management system. For today's module, I will be discussing on distributed database architecture. Some of the learning objectives for today's session include the different partitioning structures that we have been talking about, like horizontal fragmentation and vertical partitioning of distributed databases, distributed database architecture, transparency objectives, and we will talk about commit protocols. Like from the previous session, we have used horizontal partitioning where we have taken tuples into consideration for dividing all the records from the actual table, giving the replicated data to the different sites. So, different rows of a table at different sites. Some of the advantages of it include data stored close to where it is used, thereby we are ensuring efficiency. Local access optimization is provided better, thereby improving the performance. Only relevant data is taken into consideration at different local sites, thereby improving security. Unions across partitions, whereby we are ensuring ease of query. These are the main highlights of using partitioning into the distributed databases. Some of the disadvantages of using these tables: accessing data across partitions, which might lead to inconsistent access speed, and no data replication will also provide backup vulnerability. So, in similar with the horizontal fragmentation, vertical fragmentation also has the same set of advantages and disadvantages, excepting that combining data across partitioning is more difficult because it requires several join operations. When you consider horizontal partitioning, most of the selection of records will be on an operator called select, whereas when you consider vertical partitioning, it will be on the attributes. So, we will be using an operator called joins. So, it is more difficult because it requires multiple joins instead of unions. On a horizontal partition, we have used selection as one of the operator, and on vertical fragmentation we have used projection as another operator. But then to join back and get back to the original global schema relationship, we have used union on the horizontal fragment, whereas in vertical fragment we would have used joins. So, by way we are ensuring that we wanted to use multiple joins on a vertical partitioning, which could be one of the very difficult scenarios with respect to vertical partitioning. To hint on a specific example of a distributed processing system, let us consider a distributed processing system for a manufacturing company. If a manufacturing company has to process on a distributed information, it requires help of an engineering database. There would be a team which will be completely based on the design aspect of it. So, there will be CAD/CAM workstations which is completely divided as engineering department, and these are connected by engineering computers which has got a engineering database. This is connected to a computer corporate mainframe, and this corporate mainframe completely maintains its own employee database. Not only that, the manufacturing unit also has a computer which is connected to a gateway, which will be internally connected by different PCs on a local area network, which is again connected to a database server connected to a local database. And this manufacturing company has also maintains a manufacturing database. So, this is a typical scenario of a manufacturing company where it has engineering division, it has manufacturing division, and it has its own corporate division. So, now that it is the challenge that I may have to integrate all these across one particular platform. So, I can, within this organization, I can create 5 distributed organizations. One could be on a centralized database, but then I will have a distributed access. Let us maintain all the corporate values on one particular database, but then the access would be from different sites. So, it will be distributed access, but then the database will be very common. The second distributed option would be replication with periodic snapshot update. So every update that is happening, say over a month, over a quarter, or over a year, half yearly or year, will be taken and it will be updated only to those databases which requires this sort of information. Replication with near real time synchronization of updates is another scenario which actually operates on a push replication scenario. The fourth possible combination that we wish to provide is we can partition, but then this partition will be on one logical database, and the last one would be on, it can be partitioned, and these partition information will be available in a local schema which is said to be independent, and it will be again non-integrated segments. So these are the 5 different operations that we can provide on a distributed database organization platform. When we look at the distributed design strategies on these platforms, say the strategy that I would give on the initial case would be on a centralized platform. The second one will be on a replicated, but then it adopts to snapshot, which will be on a push replication strategy, synchronization replication, integrated partitioning, and decentralization with independent partitioning. So by considering these different strategies, how would you evaluate on the usefulness of these strategies? So we provide various parameters for which this strategy need to be evaluated. Parameter 1 is on the reliability, expandability, communication overhead, manageability, and data consistency. When we look at centralized strategy, the overall reliability is very poor. Why? Because it is highly dependent on only on the centralized server. So the reliability aspect of it on a network, very trafficked network, will be very poor. At the same case, if you look at the expandability, since it is all maintained on a very common centralized server, then the limitations to the barrier will be on the performance front. Communication overhead will be very high because of heavy traffic to a particular site. And talking about manageability, it is very good to manage having all the data in one particular site. One monolithic site requires little coordination, whereas data consistency will be excellent because all users always have the same data. Within the same data, maintaining consistency has never been an issue. So when we look at the centralized platform, centralized strategy, most of the performance appraisal systems have been performing very poor, whereas the manageability and consistency aspect of it is too good with respect to centralized strategy. But then altering ourselves with a distributed scenario where we wanted to replicate with snapshots, then the reliability of snapshots is good because redundancy and tolerated delays are provided because of replicated with snapshots. And when we look at a parameter of expandability, expandability will be very good. Why? Because we are trying to replicate the snapshots. So cost of additional copies may be less than the linear one. And talking about the communication overhead, it will be low to medium and it will not be too high. So it is not constant, but periodic snapshots can cause bursts of network traffic. And talking about manageability, manageability is very good because we maintain snapshots of the data. Each copy is like every other one. And data consistency, the maintenance of consistency of the data is quite medium, primarily because as long as delays are tolerated by the business needs. Talking about synchronized replication, the reliability will be very good. It will be excellent in fact. Why? Because the redundancy and the minimal delays, it provides very minimal delay. And talking about expandability, it will be very good, mainly because the cost of additional copies may be low and synchronization work on linear. Consistency overhead is medium, manageability is medium, data consistency is medium to very good, and integrated partitions, creating multiple partitions which are either a loose integration or a tight integration. This kind of partitions created would give a very good impact on the reliability aspect if it is very low. So reliability will be very good because effective use of partitioning and redundancy is being provided. Expandability will be very good since new nodes get only data they need without changes in overall database design. So any new nodes that require some information, it takes up only those information for its process rather than considering the entire database for further processing. So communication overhead is also very less and it can sometimes go to a medium state. So it most requires are most queries are local, but queries which require data from multiple sites can cause a temporary load. But then managing all this in a partition manner, since it has got few fragments that is involved, then manageability is difficult, especially difficult for queries that need data from distributed tables, and updates must be tightly coordinated. Although it takes up multiple fragments, very simple fragments on multiple locations, manageability on getting all that integrated towards one common notion will be very difficult. The last one will be on the data consistency, which will be very poor because considerable effort and inconsistencies are not at all tolerated with the integrated partition scenarios. On the other case, from a distributed environment, if I am switching myself to a decentralized environment with independent partitions, then the reliability will be very good. Depends on only local database availability. Expandability is good. It's primarily because new sites independent of existing ones, and the communication overhead will be very low and little if any need to pass data or queries across the network. Manageability will also be good, easy for each site until there is a need to share data across the sites, and data consistency is pretty much low. If you start looking at centralized databases, the consistency aspect of it is very good. But then as and when we shift ourselves to a distributed environment or to a decentralized environment, we may not be able to provide utmost consistency, but then we will be able to provide a very good reliability, expandability and communication overhead when we are shifting ourselves to a distributed environment. Talking more about this distributed database management system, distributed databases surely require a distributed management system. So some of the functions of distributed database management systems are: it locates data with distributed data dictionary, determine location from which to retrieve data and process the query components, DBMS translation between nodes with different local DBMS uses middleware. This tries to maintain utmost consistency when it is multi-phase commit protocols. Global primary control is being provided. It is scalable to any number of sites being provided, and it has to ensure security, concurrency, query optimization and recovery in terms of major failures. Let us draft a simple architecture of a distributed database stage. If you consider this architecture, this belongs to one particular site where the entire site will be maintained by a communication controller. This communication controller in turn tries to communicate through a network to multiple databases. Once when the query comes in from the application programs, then it contacts the local DBMS, and the local DBMS in turn connects it to a site 1, then it is getting distributed. Looking at the local transaction steps, the application makes a request initially to a distributed database management system. Distributed database management system checks the distributed data repository for locating where the data is actually present, finds that it is available with a particular local database. Distributed database sends a request to the local DBMS. Local DBMS processes the request and sends the result back to the application. So this has been presented here, where any query that is being presented to the application program initially sends the request to a distributed database. From the distributed database, it is being taken to a distributed data repository, which is like a data dictionary, to find out where the data is actually present. It plots to which site or to which local DBMS this data is present. Then it transfers the entire data to that particular local DBMS. From the local DBMS, it gives the query to the database. It processes the query, and the result of which is being provided to the from the local database to the application program. So this is the procedure, or these are the steps that we are trying to provide on a local transaction when all the data are stored locally. Same is not the case with all distributed databases. It will not be available in their own site. Many a times it may have to connect to a gateway, and it may have to connect to outside world through a communication controller. So the impact of communication controller now comes into point, where global transaction steps, application makes a request to the distributed database management system. The distributed database management initially checks the distributed data repository for the location of the data, finds that this data is not present in the local machine, local DBMS, but then it is available in the remote database management system. Then this distributed database management system routes request to the remote site. The distributed database management system at remote site translate request for its local DBMS if necessary, and sends the request to local DBMS. Local DBMS at remote site process the request, sends back the query to the application program. So local DBMS at the remote site sends the result to the distributed database management system at the remote site. Then the remote site of a distributed database management system sends back the results to the originating site, where from the actual query turned up. Distributed DBMS at the originating site sends the result back to the application. So if you look at the architecture on a remote site that is getting used, the system will be executing in this manner. I provide a query on an application program, then it will reach the distributed database system. It will in turn be fetched from the distributed or data repository. It finds itself that this is not available in the local database, this is available in some remote database. So the distributed database takes up the responsibility of transferring that query to a remote database by a communication controller. So the query reaches the remote distributed database management system, and this finds itself on a distributed data repository, then locates to the local DBMS. The local DBMS executes the query and gives the result back to the distributed database management system. And once the result is being fetched on this remote site, then through the communication controller it is being sent back to the actual site, and from the actual site of a distributed database management system back to the application program, this is being provided. So this global transaction transfers all the data to a remote site, rather it is not at all available in the local site. So that is the distinction between a local transaction and a global transaction. When we look at transparency objectives, although this distributed database management systems provide utmost transparency, it can either be a location transparency or it can be a replication transparency. When you talk about location transparency, user application does not need to know where the data resides. So it can connect to a remote site, the location need not be known, the system will connect it to its remote site, get all the data processed there itself and gives it back to the application program, thereby ensuring it is there available in the local database itself. This can be very well be visualized when we withdraw some amount from an ATM. The ATM will be present in the remote site, but then once we insert the card, it although sends us a message saying we have all the records available in that particular machine itself, but then it is not there in the ATM itself. It tries to connect itself to the remote server, and the remote server processes the request, sends it back. So it is because of the connectivity on the network and the faster response, we could get as though that entire detail will be available on that particular machine itself. The second thing will be on the replication transparency, where the user or an application does not need to know about duplication. So how many duplicate values that exist on the either on the local server or on the remote server need not be known, but then it has to maintain at most consistency as possible. We have one more transparency which is called a failure transparency. Either all or none of the actions of the transactions are committed. Say we most probably call these type of transactions as atomic transactions. Say by atomicity we maintain either we may have to commit to all or we may have to deny to all. So either all or none of the actions of a transactions are committed. Each site has a transaction manager, and this transaction manager has to ensure that all the queries are processed at their local DBMS and it has been sent back effectively to the global DBMS. So log transactions and before and after images are being taken. It maintains complete concurrency control scheme to ensure data integrity. Requires special commit protocols. Let us take up those commit protocols in detail. Protocol, as we might appreciate, protocols are nothing but standard set of rules that we tend to provide. As far as this two-phase commitment protocol is concerned, we will majorly concentrate on two different entities. One of the entity is called a coordinator, the other entity is supposed to be a participant. The two phases that we might know from a regular DBMS, that is from a relational database management system, will be on a growing phase and shrinking phase. On a regular DBMS, relational database management system, to do an operation of a transaction, we might provide logs, primarily because if more people are about to use on a particular transaction, then every person has to log that particular transaction, use it and unlock once they are done, so that the other person can log it. This is to basically assure on the consistency of the transaction. But then this scenario is completely changed when we come to a distributed database. When we talk more about a distributed database, we talk on the commitment protocols, which says on phase 1 we plan for the commitment and phase 2 we execute on the commitment. It so happens for blocking a particular room which has a very good facility, say video conferencing facility, initially as a coordinator I may have to request the participants whether how many of them are willing to participate for this video lecture. Then if everybody says yes, then the participants are willing to commit, then I might execute my transaction to happen. So initially I will plan for my transaction to happen, then I will start executing those things to happen. If it has been a centralized database, I can request the local database in direct, or I can request the database in direct, so that it will execute on its own. But then having distributed all the records, having replicated all the records to different locations, then it would be very difficult for me to coordinate, integrate all the participants on one particular stream, bringing them back, making them execute the entire list of transactions will be very tedious job. So the first phase of this two-phase commitment protocol would be on a preparing phase. So as a preparement phase, as I have already told you, there will be only one coordinator and there will be a list of participants which are supposed to be remote sites who are about to participate on this transaction. So in this prepare phase, the first thing that a coordinator does is, coordinator receives a commit request. Coordinator instructs all the resources, that means all the participant managers, to get ready to go either way on the transaction. Each resource manager writes all updates from that transaction to its physical log. So every participant will write in its own local database or on a log file that we may have to prepare ourselves to commit to this transaction. So coordinator tries to receive all the replies from the participants or resource managers. If all the answers from the participants are said to be okay, it writes commit to its own log. So if everybody says okay to the coordinator, then the overall transaction is supposed to be a global commit transaction. If not, if somebody else or in one of the participant or a resource manager is not about to consider this request given by the coordinator, then it writes rollback to its log. So as a participant, it writes, it will not say commit, it says rollback, and the entire commitment phase preparation is in vain. And the second phase that we are talking about is the commitment phase, where after receiving the complete acknowledgement from the participant, it is now the coordinator's responsibility to take up whether to go in for a pure commitment or a pure rollback. So with the commitment phase, the coordinator then informs each resource manager, each participant on the loop of its decision and broadcasts a message to either commit or rollback. So if all the participants tend to provide the results as okay or commit, then the message from the coordinator will be on a global commit. If one of the participants is not willing to commit for the transaction, then the message from the coordinator will be it cannot be a partial commit, it can be then be abort. So if the message is commit, then each resource manager transfers the updates from its log to the database. So a failure during the commit phase puts a transaction in a vain, in limbo. This has to be tested for and handled without timeouts or polling. In short, in this particular session, we have looked at the architecture of distributed database, but then to look at the importance of distributed database architecture, we have considered centralized and decentralized database design strategies over different parameters like reliability, expandability, consistency and other factors, whereby we have proved most of the distributed database systems will provide a very good reliable system. So for those reasons, we have shifted toward explanation of distributed database architecture. And we have explained with two different scenarios like local database management scenario and with a global database management scenario. With the global database management system, we wanted to connect to a remote machine where the request has been sent and how it has been processed. So the distributed database architecture has been responded on this platform. Then we talked about distribution transparency also. So although we maintain location transparency, we also wanted to maintain the replication transparency. So those have been a discussion in this particular session. Not only that, we have ensured all the planning that has to be executed over these distributed databases have been coming under a commitment protocols, whereby we have seen two-phase commitment protocols where we have started to initiate on a prepare phase and we wanted to have a commit phase. On a preparation phase, we as a coordinator, we will send message to all the participants and the participant has either to say okay or a no message. If he sends a okay message, then the transaction that has to be executed takes it to be a global transaction, then it will respond back saying a very positive response. When they give a no response, one of the participant on the loop gives a no response, then the entire global transaction has to take a decision of rolling back to the original status. So this is what was discussed in this particular session. Thank you.